Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 11th Physics, System of Particles and Rotational Motion, Chapter 7 NCERT Solution, Part 2. Before we start our today's class, we request you to subscribe, like and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's lesson. In the last class, we have done till question number 7.5 and today's session will start with question number 7.6. The question is, find the components along the x, y, z axis of the angular momentum I of a particle whose position vector is r with components x, y, z and momentum is p with components px, py and pz. Show that if the particle moves only in xy plane, the angular momentum has only a z component. So this problem can be solved in two steps. First step, step 1 is to find the angular momentum of the particle, and second step is put the value of linear momentum and the position vector in xy plane. The first part, step 1, find the angular momentum of the particle. So it is given in the problem that linear momentum of the particle is P is equal to Px I plus Py z plus Pz k. Position vector of the particle r is equal to xi plus yj plus zk. This is also given in the problem. We know that angular momentum I is equal to r cross p, that is position vector cross linear momentum. Now if we put the value of r and p from the above, we will get xi plus yj plus zk cross pxi plus pyj plus pzk, which can be written in the form of a determinant as ijk xyz and px py pz. Now if we equate the linear momentum as pxi plus pyj and ixi plus iyj and izk is equal to I, solving the determinant will get this solution on the right hand side. I bracket x bracket y pz minus z py minus j x pz minus z px and plus k x py minus z px. So basically, if we compare the coefficient of I, j and k, we will get, for example, this should be equal to this. So similarly, coefficient of y in left hand side should be equal to coefficient of j in left hand side should be equal to coefficient of j in the right hand side. So we can get this equation first as a ix is equal to ypx minus zpy, iy is equal to xpz minus zpx, iz is equal to xpy minus ypx. Now coming to step 2. In step 2, we'll put the position vector and linear momentum values in xy plane. Hence the z component of the position vector and linear momentum vector becomes 0. Therefore z is equal to pz is equal to 0. Putting these values of z and pz as 0 in equation 1, we get ix is equal to 0, iy is equal to 0 and iz is equal to xpy and ypx. Therefore, when the particles are confined to move in xy plane, the direction of the angular momentum is always the z direction, always along the z direction. Let us move to the next problem. So the next problem is 7.7. Two particles, each of mass m and speed v, travels in opposite direction along parallel lines separated by distance d. Show that the vector angular momentum of the two particle system is same whatever be the point about which the angular momentum is taken. Let us see the solution. So we'll solve this problem in steps. First step is draw the diagram. Second step is find the angular momentum and compare them. So let us draw the diagram as given in the problem, and we'll write the physical quantities which are available or known to us from the problem. So let at the certain instance two particles be at point P and Q as shown in the figure. So one particle is at point P and other particle is at point Q. So next step is find the angular momentum and compare them. So angular momentum of the system about P LV is equal to mv multiplied by 0 plus mv multiplied by d. So it is equal to mvd. Angular momentum of the system about Q point Q is equal LQ is equal to mv multiplied by d plus mv multiplied by 0, that is mvd. This is equation number 2. Consider a point R1 which is at a distance y from point Q, that is QR is equal to y. So PR is equal to d minus y. We can see the same in the figure to get a clear picture. So here QR is equal to y. So let us see the sum again. So PR is equal to d minus y. Angular momentum of the system about point R, LR is equal to mv d minus y plus mv multiplied by y. Upon solving, we get mvd minus mvy plus mvy get cancelled out. So we have till now we have found the angular momentum at the point R. Comparing equation, so comparing equation 1, 2 and 3, we get angular momentum at point P which is PLP, angular momentum at point Q, which is LQ, and angular momentum at point R, which is LR. All are equal. Therefore, LP is equal to LQ is equal to LR. This is equation number 4. We infer from the equation 4 that angular momentum of a system does not define on the point about which it is taken. So let us move to the next question. So our next question is 7.8. A non-uniform bar of weight W is suspended at rest by two strings of negligible weight as shown in the figure 7.39. So this is figure 7.39. The angle made by the strings with verticals are 36.9 degree and 53.1 degree respectively. The bar is 2 meter long. Calculate the distance d of the center of gravity of the bar from the left end. Okay, let us see the solution. So the first step is step 1, draw the free body diagram. So we have drawn the free body diagram. The main part of the diagram is the tension is divided, T1 tension T1 is divided into horizontal and vertical components. Again, tension T2 is also divided in the same way, vertical and horizontal components. Now after drawing the figure, we will evaluate the torque about the center of gravity. So how can we do that? So we'll write all the information which are given in the problem. Length of the bar L is equal to 2 meter. T1 and T2 are the tensions processed or produced by in the left and right string respectively. At translational equilibrium, we have T1 sine 36.9 degree is equal to T2 sine 53.1 degree. So if we do the cross multiplication, so T1 and T2's ratio can be found as sine 53.1 upon sine 36.9. Once we put the values and of sine 53.1 and sine 36.9, we get 0.8 upon 0.6. Upon solving, we get 4.3. Therefore, T1 is equal to 4 upon 3 multiplied by T2. So, for rotational equilibrium, on taking the torque about the center of gravity, we have T1 cos 36.9 multiplied by D, T2 cos 53.1 multiplied by 2 minus D. Now we can write T1 cos 39.9 multiplied by D, T2 cos 53.1 multiplied by 2 minus D. Again, upon solving, we can find that all the values are known, only D is not known, and we can find the value of D in this case. So ultimately we get the value of D as 0.72 meter. Hence CG, center of gravity of a given bar, lies 0.72 meter from its left end. So this is the end of this problem. Let us start with the new problem. So our next question is 7.9. A car weighs 1800 kg. The distance between its point and back axis is 1.8 meter. So figures which are given is the weight, which is 1800 kg. The distance between the back and front axle is 1.8 meter and center of gravity as 1.5 meter behind the front axle. What we have to find? We have to find the force exerted by the level ground on each front wheel and each back wheel. So let us see how to do this sum. So this sum can be solved in steps. First step, write the physical quantities which are given in the problem or which are known to us. So mass of the car, which is given as m is equal to 1800 kg. Distance between the front and back axle d is equal to 1.8 meter. Distance between the CG, center of gravity, and the back axle is 1.05 meter. Now in the second step, we'll draw a free body diagram according to the problem. So as far as the free body diagram, so now it is clear that in step 1 we have written all the known physical quantities. In step 2 we have written we have to create a free body diagram which is given as below. So here the important point is we'll write the values of the known figures which are given. So and these are the two reaction forces. So various force acting are shown in the figure. So let us move to step 3. So RF and RB are the force exerted by the level ground on the front and back wheel respectively. The translational equilibrium at translational equilibrium Rf plus Rb is equal to mg. So mass is 1800 plus g is multiplied by g is 9.8. Upon solving we get 17640. For rotational equilibrium, on taking the torque about the CG, we have Rf multiplied by 1.5, Rb multiplied by 1.8 minus 1.5. Rf multiplied by 1.5 is equal to Rb multiplied by 0.7. Therefore, Rf upon Rb is equal to 0.75 upon 1.05. Upon solving, we can get 5 upon 7. So Rf upon Rb is equal to ultimately 5 upon 7. So Rb is equal to 1.4 multiplied by Rf, which is equation number 2. Solving equation 1 and 2, we get 1.4 Rf plus Rf is equal to 17640. So if we want to find out Rf, then we can get 17640 upon 2.4, which is equal to 7350 Newton. Now Rf is equal to 1740 upon 2.4, which is 7350 Newton. Then Rb is equal to 17640 minus 7350 is equal to 10,290. Now, therefore, the force on each front wheel is equal to will have to divide it by 2, that is 7350 divided by 2, which is equal to 36575 Newton. And similarly, we can find out the force exerted on each back wheel is equal to 10,290 divided by 2, that is 5,145 Newton. Let us see the next problem. The next problem is 7.10. So it has two parts, part A and part B. Let us see first part A. Find the moment of inertia of a sphere about a tangent to the sphere, given the moment of inertia of the sphere about any of its diameter is 2 mr square upon 5, where m is the mass of the sphere and r is the radius of the sphere. And the second question is, in the part B, we have given that the moment of inertia of a disk of mass m and radius r about any of its diameter is mr square upon 4. Find the moment of inertia about the axis normal to the disk and passing through a point at its edge. So let us see the solution. So we'll solve it in few steps. For example, first step for part A is draw the diagram and write the physical quantities which are given to us. So the diagram is drawn as below. So we know that the moment of inertia is 2.5 mr square about the diameter. It is given in the problem. So it is given that moment of inertia of sphere is 2 by 5 mr square. Let us see the next part. Now we will apply the theorem of parallel axis. So what is theorem of parallel axis? So according to the theorem of parallel axis, moment of inertia of any body about any axis is equal to the sum of the moment of inertia of the body about a parallel axis passing through its center of mass and product of its mass and the square of the distance between the parallel axis. So this is the definition. First we have written the definition, and according to the definition we have written the derivation here. So let us see the derivation. So moment of inertia about a tangent of a sphere is 2 by 5 mr square. This is about the diameter, and this mr square came from the theorem of parallel axis, and we add it, we get 7 by 5 mr square. Now let us see 7.10b. Step 1. Draw the diagram and write the given value. The moment of inertia of the disk about the diagram is about its diameter is 1 upon 4 mr square. So in step 2 we'll apply the theorem of perpendicular axis. So according to the theorem of perpendicular axis, the moment of inertia of the planar body about its perpendicular to its plane is equal to the sum of moment of inertia of the two perpendicular axes concurrent with perpendicular axis and lying on the plane of the body. So according to the theorem we get 1 upon 4 mr square plus 1 upon 4 mr square. Upon solving, we get half mr square. Applying the theorem of parallel axis, we get the moment of inertia about the an axis normal to the disk and passing through the point of its edge is half mr square plus mr square. So it is 3 by 2 mr square, and this is the answer. So this is the end of today's session. Before we close, we request you to subscribe, like and share our channel among your friends and families. Please click on the subscribe button to support us, and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for your support and watching our videos. Thank you very much.